let's look at salts that dissolve in water and how we can determine what their pH is going to be. In a separate video, we'll look at other acid-base topics that have to do with the structure of the molecule. But for the soluble salts and their pH, the key word is hydrolysis, which of course comes from the Greek hydro meaning water and lysis meaning splitting up. Now, if you think of the word hydrolysis, you may think of salts just dissolving in water. And we know, of course, that the negative end of the water molecule, the polar water molecule, is attracted to the cation of the salt, and the positive end, or hydrogen end, is attracted to the negative, or anion, in the salt. This, however, is not hydrolysis. This is dissolution. The other word that we have used for dissolving salts is solvation. And here you see the process visualized where water molecules are surrounding the cation and the anion of the salt. And again, this is not hydrolysis, this is solvation. Hydrolysis occurs when a salt not only dissolves in water but also reacts with it. The ions, cation or anion, are good enough acids or bases to break up the water molecules. So let's look at the first reaction. Acetate, CH3COO-, and water. Here is the acetate ion on the left and the water molecule on the right. When a collision occurs, very often, the hydrogen ion of the water is attracted to and bonds to, covalently, the acetate, making acetic acid, and of course it leaves hydroxide behind. Let's look at that again. Here's the before picture, that's the reactants, and here are the products. You can write that down as a chemical equation. Acetic acid is a weak acid, and acetate, its Bronsted-Lowry base, is a strong base, the conjugate base. So this is a favored situation, the acetate turning into the acetic acid, leaving behind the hydroxide. That means that adding acetate ion to water will raise the pH because it leaves behind hydroxide ions. It's a basic salt. Now let's look at the Ka for acetic acid. You may be familiar with it. The Ka, of course, expression, hydrogen ion times the acetate divided by the remaining or equilibrium concentration of the acetic acid. We can also look at the reaction we just looked at, the reaction that produces acetic acid and hydroxide ion, and the product here, acetic acid and hydroxide, is the numerator, and the acetate ion at equilibrium is the denominator. And that Kb, we'll see, is 5.6 times 10 to the negative 10th. Now let's do something. Just take a moment with your calculator and multiply these two constants, these two numbers together, and then turn the video back on. The product, of course, is 1 times 10 to the negative 14th. That's Kw. That's the equilibrium constant for the breakup of the water molecule into hydrogen ions and hydroxide ions. So we can actually generalize and say for any conjugate acid-base pair, like acetic acid acetate, Ka times Kb is equal to Kw. That's a useful piece of information now, because that means that if we want to find Kb for, say, propionate, we just divide Kw by Ka. Let's look at an example. Quinoline has the following structure. If you look carefully at it, you may be able to see what feature of the structure leads us to call it a base. That feature, of course, is a lone pair of electrons. These are capable of attracting hydrogen ions, and the hydrogen then would stick covalently to the lone pair of electrons and make a covalent bond between the nitrogen and the hydrogen, and that means that this original molecule of quinoline is a base. something that accepts protons. Now its conjugate acid has a pKa of 4.9. So what is the base dissociation constant of quinoline? Use the method we just showed you. The easy way to do this is to see that the pKb is 14 minus 4.90, which is of course the pKa. So the pKb is 9.10, and that means that the Kb is 10 to the negative 9.10, or 7.94 times 10 to the negative 10th. So that's what you do if you have the Ka to find the Kb of the conjugate base. Let's look at a lab that you may have done, or something you may have done similarly, where we have taken 4 salts and dissolved them in water at the same molarity. And as you can see, the acid-base indicators, the same indicator, methyl bromthymol blue here and then methyl red here, show that the pHs are different. As you go from left to right, the pH goes from 7 to 3.5. Sodium nitrate at 7, aluminum nitrate at 3.5. So stop the video and think about this for a minute and ask why, if you know something about the strength of the base formed by these metals, how does it make sense that this pH is arranged as it is? Well, if you think carefully about it, you see that the nitrate here does not affect the pH, because nitrate is simply a spectator ion whenever it's put into water. It hardly ever does anything because it is a very low energy ion. The calcium, however, ion, the Ca2+, introduced into water, will steal some of the hydroxide from the water, leaving H+ behind, surrounded by its water. Even more so, aluminum, when it is added to water, the aluminum ion, Al3+, can scarf up as many as 3 hydroxides from the surrounding water molecules, leaving hydrogen ions behind. And as you can see, the 3.5 pH shows a pretty high acid content. So the nitrate does nothing to the pH, but the other ions can. Now we see in a previous slide that anions like acetate that are conjugate bases of weak acids like acetic acid will of course increase the pH by hydrolysis. And in some occasions you have anions that are conjugate acids of weak bases. You've seen some of those before, especially the polyprotic acids. They will decrease the pH by hydrolysis. You can find examples in your textbook. The other thing to understand is that cations of strong Arrhenius bases like sodium, lithium, potassium, barium will not affect the pH because those act as spectator ions when put into water. But other metallic ions that form less soluble and weaker bases, calcium, zinc, aluminum, copper, manganese, they will cause a decrease in the pH by hydrolysis by scarfing up hydroxide ions from the water and leaving hydrogen ions behind. Now, just in passing, when a solution contains both a conjugate base of a weak acid and the conjugate acid of a weak base, there will be an effect on pH, but it depends on the Ka and Kb values of those species. You will not have to do any calculations for that in most courses. Remember, in the tug of war between acids and bases, the strong guy wins. Now for some practice. What effect will adding each of these ions to a solution have on the pH of the solution, remembering the rules you just learned? Turn off the video, work it out, and then turn the video back on. Here are the answers. Nitrate has no effect, just like chloride or sulfate. Carbonate of course, can form with the water the weak acid carbonic acid. The ammonium ion can scarf up hydroxides from the water molecules, leaving hydrogen ions, and so that's going to lower the pH. Here's the sulfate, no effect. Here's the potassium, no effect because potassium hydroxide is a very, very strong base. Iron 2, however, will lower the pH because the iron 2 ions interacting with the water will attract the hydroxides away from the water and leave hydrogen ions. Here's some more practice. For each of these following salt pairs, indicate which salt would form the more acidic or less basic 0.02 molar solution. Turn the video off, work it out, and then turn it back on. Here are your answers, and I hope that it's a little more obvious now after you've gone through the video as to why these 1, 2, 3, 4 salts would give more acidic solutions. In the next video, you will study the structure of acids and how strong they are, what their pKa is.